Hello.
Hey,
Yeah. So you wanted to finish the electrocyclic reactions, like the electron like ring closing and
yeah.
ring opening. Yeah. So this is the chart of like the Woodward-Hoffman rules, where if we have an even pair of electrons participating in the reaction, or an odd pair of the reactions, we would either be conrotatory or disrotatory, depending on if we have heat or light on the arrow. So what conrotatory and disrotatory means is that in the direction we rotate the groups in, the electrons in. So conrotatory means that we are going to rotate the groups in the same direction.
Hmm.
Right? Same direction. And we're going to rotate it in the direction of either um, counterclockwise or clockwise or counterclockwise. Right. This rotatory would mean that we are going to rotate the groups on the opposite direction. Groups on the opposite direction. Right. So there's a thing called the thumb rule that I like to do to figure out the stereochemistry behind these reactions. And there's going to be two types of electrocyclic reactions. There's going to be ring closing versus ring opening, right?
hmm
So your thumbs, they're going to start a certain way depending on what reaction you want to do, and they're going to end a certain way, right? Where if we're trying to close the ring, our thumbs are going to start either left or right, like this, and then they're going to end up or down like that to tell if it's going to be wedge or dash. If we're ring opening, we're going to start up or down depending on if the groups are wedge or dash, and then we're going to end our thumbs right or left to show where the groups are going to be relative to each other. And I'll go over an example of that, but um, if we are ring closing, our thumbs are going to start either left or right and end up or down. Ring opening is going to be the opposite of that. We're going to start our thumbs up or down and end our thumbs left or right. Okay. And in all of these reactions here, we always rotate clockwise or counterclockwise. Okay, so let's look at an example. We see here that this ring is going to be a ring closing reaction because we don't have a ring to begin with,
hmm
where we see that I'm going to make a dashed line here. That's the new bond that's going to be formed right there from one of the double bonds here. I'm just going to say that this double bond makes a bond right there, moving this double bond to make a double bond there. And then this double bond makes a double bond there. Let's draw in the template right here where we have this structure here. We still have the methyl groups on this carbon. Wait, hold on. There's something else.
Wait, it wouldn't be a double bond, right?
Yeah,
On
yeah, it
the
wouldn't be a double bond, right? It would be a single bond because, yeah, that's right, it's a single bond because this is the new bond that we formed right here. Right, right. Where the methyl groups here could either be wedge or dash. And since we are ring closing, how many electrons are participating in this ring closing reaction here?
6.
Yeah, six, which is an even pair. Oh, an odd pair, because there's
It's not-
three pairs of
it's-
electrons. One, two, three, right? So if we have an odd pair of electrons and we are reacting it under light, H nu, odd pair under light, H nu, is a conrotatory reaction, which means that we're going to rotate the groups on the same side. So notice how the methyl groups are facing away from each other.
Uh-huh.
So we are ring. closing here. So we're gonna start our thumbs away from each other like that. My left thumb here is facing to the left side. My right thumb here is facing to the right side because they're facing away from each other.
Mhm.
Uh, we said this reaction was, what was it again? Odd pair, light,
We said it was
conrotatory.
yeah.
Right. If I chose to rotate my right thumb clockwise, that's gonna go down like that, right? My left thumb would have to go clockwise as well because they're on the same direction. I'm gonna end my thumb where it goes either up or down first. If I rotate my right thumb clockwise, it goes down first. If I rotate my left thumb clockwise, it goes up first. So you notice how they're trans to each other. One is up and one is
Yeah.
down, right? So that's how you tell the stereochemistry between those two.
Okay. Does it
They
matter
are,
which of the groups you pick to be? I mean,
yeah,
in this case, they're the same, the methyl, but like, let's say maybe one like was a methyl or one was an ethyl, then would it matter which one you put wedge, or it's just plus an enantiomer then,
yeah,
right?
yeah, yeah. It would be plus enantiomer then, right? That's right. Right. So for this example here, it's the exact same thing, but now we have different groups. There are still three pairs of electrons, an odd number, but this time we have heat. The direction changes. Where if we have heat, the reaction is going to happen under disrotatory conditions. Right? Where this is the template right here. And we know that they are facing away from each other. So let's start our thumbs away from each other because we are ring closing here. Right. If they are just rotatory, they're going to rotate opposite directions. If I rotate my right thumb clockwise, that's going to hit down first. So I'm going to stay that down. That means that I have to rotate my left thumb counterclockwise because they're this rotatory, opposite direction. If I rotate it counterclockwise, that's also going down. So now they're cis to each other,
Mm-hmm.
right? Like that. And
You're to just go if you're to go clockwise instead, on one way and then counterclockwise on the other way, it would be the wedge.
right, uh-huh. That's right,
Yeah.
that's right.
Sorry, on the other way. Yeah.
Mhm. Yeah.
You could say plus an enantiomer for these, right? Instead of
Yeah,
drawing them out.
right, right. You could say plus enantiomer for these because we have no pre-existing chiral center, but if we had an R group here with an chiral center, then we can't say plus enantiomer in that
Yeah.
case.
Okay.
Mhm. Okay. For this next one here, this one looks a little bit weird. But this is going to be a ring closing still, where we're gonna make that new bond right there. We're gonna move
Because
that.
in this case, we're dealing with 4 pi electrons, so we know we have to be making like a cyclobutene or
Yeah,
some.
cyclobutene. That's right. 4 electrons moving cyclobutene there. That's right. And the other ring is a 1, 2, 3, 4, 5. Wait, it doesn't start there. It's actually gonna start here, the other ring. 1, 2, 3, 4, 5, 6, 7, 8 membered ring. Right? But we don't know if it's gonna be wedge or dash on this sp3 carbon right here. We know it's 4 electrons, like you said, reacting, which is an even pair, reacting under light.
Yep.
Yep.
So then that would be even and light disrotatory.
Yeah, disrotatory.
Disrotatory.
Uh-huh.
In this
Disrotatory.
in
Right. They are both facing in. So our thumbs will start this way instead, like where they're
yeah,
pointing to each other like that. One will rotate clockwise, one will rotate counterclockwise,
yeah,
right? And that makes them cis to each other. The way I did it, they're both facing up, but they could all go the other way as well, making them dash.
yeah.
Okay. this case, we are still ring closing. We're still going to make that cyclobutene because 4 electrons are moving an even pair, right? And this time we're reacting this under uh light, which is still disrotatory,
That's right.
right? But now our thumbs will start like this because they are facing away from each other. This CD3 group is facing up that
Uh,
way. This H3 is facing
methyl-
up that way. So they're facing in the same direction like that.
oh, wait, can you
Like
say that
that.
again?
Right. So you know how the CD3 here is facing in the direction going up like that? Right. This CH3 group here is also going up towards
Okay, yeah.
um the thing. If the CH3 was going down this way, then they would face opposite direction. But we see the CH3 is also going up. So they would face in the same direction where we start our thumbs in.
How come you don't start with them both like straight up like your thumbs?
Oh, right. Because when we are ring closing here, the thumb
Oh,
rule
you're
is that we
starting with
start left,
right.
right, or yeah,
Okay.
right. And then we always end up or down to show if it's wedge or dash. If it's going up, it's wedge. If it's going down,
Oh,
it's dash.
okay. And then
Yeah.
does it matter like let's say they are both pointing up, could you both turn them to the right as long as you follow like whether it's disrotary or conrotary?
Oh, like if one is a wedge preferred over
Or
the
like
dash.
like let's say in this case you said they're both pointing up and you point them like that. Could you also point both of them the other way? Would that
Oh
work
yeah, you
too?
could also point it up and the other way as well.
Okay. So
Right.
as long as you like follow or like consistent, it doesn't matter what direction your thumbs initially started.
Yeah, yeah. As long as you're consistent.
Okay.
Oh, right, right. I guess I see why that was confusing now because the way like I said they're both going up like it sounds like they should both start up
Yeah,
on the
yeah.
thumbs. Right, right. The both the direction up is just showing that they are going on the same direction. Where if I do the thumb rule, they have to be in the same direction, either this way or this way, right there. Yeah,
Mm,
yeah. Ding. Yeah. Up, it could have been down as well. Like if they're both down, that's still same direction. But if this was D3 was going up, and then let's say the metal group wasn't like that, but the metal group was going down, that makes it opposite from each other. So when we do the thumb rule, they would have to be opposite from each other like
yeah.
that.
Okay, I
Right,
see.
right. So it's not like up or down where we cite our thumbs up or down. It's just the relative direction.
Got it.
Mhm.
Okay.
Right. So let's start our thumbs on the same direction. Doesn't matter. It could be this way or this way. I'm gonna do this way here. They're disrotatory, meaning that one is gonna rotate clockwise, the other one is gonna rotate counterclockwise. So we see that we end in the trans configuration where one is gonna be wedge, one is gonna be dash.
Got it.
Right. So let's say this is CD3. I make that a dash, and I make this into a wedge. And we could say plus enantiomer. Okay, now this is the first example where we see ring opening now.
Okay.
Where to do this, I'm going to move that double bond to make a double bond between those two carbons. And then this single bond right there is going to break and make a double bond between these two carbons here. Right.
Yeah.
So in this case, there are still two pairs of electrons participating. One pair from that double bond, and the other pair from this single bond right here. So that's still 4 electrons, 2 pairs, even pair. Right. The template will look something like this. Right. Where the CD3, we don't know where that's gonna go. It could either go up here or down here. The CH3, we don't know where that's gonna go. It could go up here or down here, relative to each
Right.
other. To know that, to figure that out, we use the thumb rule. In ring opening, we start our thumbs up or down. Right. But first, let's figure out if this is disrotatory or conrotatory first. Where we have 4 electrons, which is an even pair, and we have heat, which is going to be even pair heat conrotatory. So we're going to rotate same direction. Conrotatory. Right. Since the groups are starting trans from each other, I'm going to start one thumb up, one thumb down because we see that they're trans from each other. When I rotate clockwise or counterclockwise, I have to end where it's left or right. So let's say that I rotate this right thumb that's going up. clockwise. It ends to my right side here. That means that the other thumb has to go counterclockwise. So this is also going to the right side, meaning that they are going in the same direction.
Okay, so you rotate them both either clockwise or counterclockwise. Or
Wait, wait. Let me see here. Wait, did I do this right? Let's see. Well, there are trans, meaning up when it's up, when it's down. This is conrotatory because this is even pair, and we have heat, so conrotatory. Oh, so this is conrotatory, not disrotatory. I rotate them in the opposite direction. We have to rotate them
yeah,
in the same direction. Yeah, right. Same direction. I did it wrong. Wait, so start trans. If I rotate this
so
clockwise,
I think they're going in together. Or I think we going out. Okay.
yeah, there would be both going out like that. Um, like, well, in this case, it does matter if we rotate clockwise or counterclockwise. If I rotate it clockwise, right, they would be pointing away from each other, which is like this right here. CD3, CH3. This came from when I rotated it clockwise. If I rotated it counterclockwise, starting one up, starting one down, let's say I go counterclockwise this way, this would also have to go counterclockwise this way. Now you know how they're like pointing towards each other.
Yeah.
Yeah, so in ring opening, the way you rotate it, clockwise or counterclockwise, does change the relative stereochemistry.
Okay.
Where
So when you draw both products then?
yes, you draw both products, but one product would be major over the other.
Yeah, because and I'm assuming it'll be the left one because the right one is steric hindrance.
Right. Steric hindrance. This one is major because less sterically hindered. Nice. Where in ring closing, it didn't matter if you rotated it clockwise or counterclockwise because you still get like either both of them would be cis or trans for ring closing.
Yeah.
For ring opening, you have different products. They could both either go out away from each other or towards facing each other, right?
Yeah. I see.
Mhm. So ring opening is the one that we have to be careful of. Ring opening is the tricky one.
Yeah.
Yeah. Mhm. Let's try this ring opening one here.
See F3. Okay, so these would go this way. This would go. Or no, that would go that way. This would go up.
Right.
Okay, so it's four,
Mhm.
and then it's using. Was it using light or heat? I didn't see.
Yeah, he
It was using heat. Okay,
yeah,
so that means that it would be conrotatory.
right, conrotatory.
And then they're both starting down. So you
Yep.
could start with the thumbs down.
Both thumbs
And
down.
then direction going clockwise. Clockwise. Okay, so I end with two pointing in the same direction. And
Hmm.
then same thing with counterclockwise.
Right. But those two will be different because we have two different groups here. One is a D group, one is a CH3 group. Hold on. D CH3, where um both going down, I rotate clockwise this way. This is the clockwise one. This is the counterclockwise one. Counterclockwise, right? Where the major product will be the bulkiest group on the out group. Our bulkiest group here is this methyl group, right?
Hmm.
And we want the methyl group to be on the out group, which is this right product here, which makes that our major product, and this our minor product because of steric hindrance. This has
Okay.
more steric hindrance because it's closer into like this system here.
Okay.
It's
And
more
then
crowded.
um like when you're like starting with both of them down and then you're turning it like let's say clockwise and like one's like kind of pointing. I mean, technically, I feel like you could say like one of them is pointing out, or like, and then you rotate them both, like how we did on this problem,
Oh, right. Uh-huh.
like how we ended up with our thumbs. Could you like technically look like down on the molecule? Because then once it's kind of
Mm.
like see how like one of the CH3s is like pointing in, and then
Yeah.
and then the other one's like kind of out. Isn't that also like I don't know how to explain it. Here, let me
Oh, wait, this is CF3, not CH3.
or CF3.
Yeah. But it's still the bulkiest group.
Let me see if let me see if I can see my thumbs. Okay, like picture like these are my thumbs,
Yeah.
and then you're rotating it like this, and then let's say
Uh-huh.
like this is D and this is CF3, and like you're looking down on the molecule like this way.
Oh, right. Yeah, yeah.
Would
If you're
that
looking
would
at it
that,
down that way,
would
yeah,
that
that's
work?
more 3D thinking. If that makes sense to you, then I would think of it like that way as well.
Yeah, I feel like that helps me understand, at least like from this perspective, helps me understand a little bit more.
Right. Yeah, that's good. Do you have
Okay.
a model kit or like have you tried it with the model kit?
I haven't tried it with model kit, but maybe I'll try it because we got one for free for 118A.
Oh yeah. Let's see. See. It's good. Yeah. Hmm. Right. 3D thinking. Yeah, because all of this 3D stuff in OChem like is useful for like the like pre-health stuff like medical school, pre-vet, because you gotta know like the relationship between like organs and like what's um like in there like spatially. Yeah.
Mm.
Yeah. Right. Let's do more practice. This is ring opening where the arrows are gonna look like that, giving us this. We have an even pair of electrons under light, which is going to be even pair under light,
Yeah.
disrotatory. Let me get this table with me. This table is useful.
Yeah.
Yeah, disrotatory.
This.
So we see that the two methyl groups are, yeah.
Or you could end with them both
Uh,
or counterclockwise, like either both out or both in.
yeah, both out or both in. Disrotatory, where they are facing away from each other. So it could be like this or like that, right? Where in this case, this rotatory, one can go clockwise, one can go counterclockwise, both out, or this way, this way. Wait, no, yeah, this way. Yeah, both out. In this case, since these methyl groups are identical, the same group, then there's no major minor. They're the same exact molecule, just rotated or flipped upside down.
Okay, let me do this thumb thing again. Okay,
Yeah,
so
uh-huh.
like this, and
Yeah.
we're moving. So if we're moving clockwise, both of them, then you could end
Oh,
up like, or
we're gonna do
there's
this
one
rotatory.
clockwise, one counterclockwise.
Right, right. Uh-huh.
Oh, okay. So then that means you'd be like this is clockwise, and this is counterclockwise,
Right. Where they're facing on the same
or
side.
or it would be like this.
Yep, or like that. Right.
Oh, okay. I see. So I did con and I got like both. I was confused. Okay, that makes sense then. Okay,
Right. It would be con if you had heat.
it was heat. Okay,
Yeah. So that's why these things could be different depending on heat or light. Right.
got it.
Mm-hmm. Next. Disrotatory. There. Okay. Okay. Let's do this one. Oh, what the heck? This is weird.
Yeah, both are on the same side.
Oh, so what the
How'd you even?
mm, what they put as the answer was butyl up here, methyl here, and then they just switched it
Yeah,
like methyl.
I was about to say, because if it opens both ways, then you could just have both of those happen.
Yeah,
Like you got it respective to only like the one carbon.
right.
Yeah.
Because we made an sp2 carbon from an sp3 carbon. Before that sp3 carbon has stereochemistry, but we um made it flat and planar by opening up the ring and making that carbon sp2 and flat. Why when we
Yeah.
do that, they have they could either be on either way when that reaction happens. Like the metal could go up or down. The superheater could go up or down.
Okay.
But there is a major and minor product here because of steric hindrance.
Yeah, I think the left one would be the major because you don't want the
Mhm.
terpene oxide going inwards because
Yeah,
it's
that's right. Nice. Okay, now this goes into aromaticity, uh, which he did not start the chapter on yet.
this is like
But
chapter 50.
yeah, this is
Yeah.
chapter 15 stuff. That was the end of chapter 14. This is the beginning of chapter 15 here.
Okay.
Right. Where I could pull up my notes and go over this stuff.
Sure. Yeah.
Yeah.
I think that'd be useful. Just because I mean he's starting it anyways tomorrow, so
Yeah.
might as well.
Mhm. Gotta go over this tomorrow too for the tomorrow's session. Yeah, let's see. Okay, so this right here, we're gonna use another useful table. There are gonna be three different categories: aromatic, anti-aromatic, and non-aromatic. Right.
Okay.
So for aromatic, you need to have an odd pair of electrons. So like either like two electrons from one pair. If it's three pairs of electrons, that's six electrons, but an odd pair. Odd pair of electrons. Anti-aromatic will have an even pair of electrons. And non-aromatic can have either odd or even pair. Right. So to be considered aromatic or anti-aromatic, you need to fulfill three conditions. They need to be cyclic in a ring. They need to be planar. And the last condition is that they need to be fully conjugated, meaning that they could do resonance throughout the whole ring.
Hmm. And that's just in general aromatic, anti-aromatic, non-aromatic.
For
Or is this just for
anti-aromatic and aromatic only. If one of these conditions are not met, then you are automatically non-aromatic.
oh, I see.
Right. But once you fulfill these three conditions, then you look at how many electrons you have, like an odd pair or even pair, and then that's how you differentiate the two, aromatic versus anti-aromatic.
Okay.
Right. And my iPad is like so buggy right now. Oh my gosh. Okay. Yeah. So this is the table we are going to use, right? Where the non-aromatic is missing one or more of these three conditions here. Okay, let's look at some examples before we try that. Let's look at benzene ring. I think you already know the answer of this, like if it's aromatic, anti-aromatic versus non-aromatic. Uh, right, which is going to be aromatic, and the reason why is because it is cyclic, it is planar, everything is sp2 hybridized, and it is fully conjugated. All of these double bonds can do resonance throughout the whole ring, right? And once it fulfills all of that, now we have to count how many pairs of electrons are in that system, which is 1, 2, 3 pairs. 3 pairs is an odd pair, so that is aromatic. Right? Aromatic. Right. Okay, let's look at another example, and now have you try this one here.
All right.
Mhm.
Oh, also, I guess this is gonna help me figure this out.
Mhm.
But for being fully conjugated, does that include a lone pair?
Yes, it
Lone.
does. It does. Yeah.
Okay.
Where on the exam, you most likely won't see the lone pair, but it's implied that there's a lone pair
Yeah.
there.
Okay. Okay. So would this one be anti-aromatic?
Right. So this is cyclic. That checks out. It is planar. It is fully conjugated. But now we have to see how many pairs of electrons are participating in the resonance. We have
Oh,
one,
how many pairs?
two, three
Okay.
pair.
Okay, so it'd be aromatic as well.
Yep. Aromatic as well. Where that lone pair counts as a pair that's participating in the conjugation. Aromatic. Let me give you the uh tricky example that professors like to give sometimes. Let's say we have this structure here. Right. You notice how this is cyclic, this is planar, and this is fully conjugated.
Yeah.
The p orbitals of these two atoms here are already taken up because if there's a double bond between that carbon and nitrogen already, this lone pair is not on a p orbital. This lone pair is going to be on an sp2 orbital. That means that this lone pair is not resonating. It's not going to participate in resonance, right? Because the thing that is resonating is the pi bond here between that nitrogen and carbon right there. In the previous example, the lone pair on this nitrogen was on a p orbital because
Okay.
it was able to do resonance with that structure right there.
And that's because it wasn't directly between that nitrogen and that carbon.
Yeah, it wasn't there was no double bond between carbon and nitrogen there. No double bond between that carbon and nitrogen there. There was only a single bond, which allows it to do resonance and make a double bond there. Right?
Mhm.
But in this case, this double bond can't make a triple bond there. There's already a double bond there, blocking the way for resonance. Right? So this will not count as a pair of electrons. The things that do count are these three pairs here. So we don't count that as a pair. Only these three pairs count, which is an odd pair, making that aromatic.
Okay.
Right. So let me give you another example here.
Would this one also be an aromatic?
Yes, because we have lone pair, 1, 2, 3, 4, 5, 5 odd pair, aromatic. Yes. Okay, let me give you some different ones, different ones that are aromatic. Let's see. Okay, let me give you uh, 1, 2, 3, 4, 5, 5 double ones. Okay. After these five, I'll give you two really weird ones for this one, and then we'll try the worksheet.
Okay.
Get water. Wait, quick.
All right.
Yeah, this might be helpful. Let me put the table nearby.
And then the first I did the rest. I'm not sure if they're right, but the first one I was just struggling with like doing like the resonating arrows, like so I could try to tell the one that's
Mm-hmm.
like cyclic structures.
Mm-hmm. Right. Yeah. So the first one here, it is cyclic because all of these atoms are in a ring, so that checks out. It is planar because all of these carbons here are sp2, and it is fully conjugated because since all of these are sp2 hybridized, there is a network of adjacent p orbitals.
Oh, so that's just okay. What I was doing to check to see if it was like conjugated was drawing like the resonant. I didn't know you could just yeah. Okay, so if they're all just sp2, then it's fully conjugated.
Yes, yes. If it's all sp2, it's all conjugated. You don't have to do all those resonance arrows to
Okay, okay,
check
that's
that.
okay. That's good to know.
Yeah, yeah. Did you try drawing all the resonance?
For the top one, I was trying to like draw all the arrows to see where how to get like the electrons flowing, and then I was like,
Oh, yeah,
is it
yeah. Yeah, yeah. You don't have to do that.
okay?
Mhm.
Okay, so if that's fully conjugated, then 1, 2, 3, 4, 5, 6, and then it's even. So this would be anti-aromatic.
Anti, because we have six pairs. Wait, 1, 2, 3, 4. Yes, which is an even pair. Even pair, anti-aromatic. Nice. Uh-huh.
And then as to the next one was non-aromatic.
Uh-huh. That and which one of these does not fulfill?
It's not fully conjugated.
Right, because we have a sp3 roadblock that blocks resonance, not fully conjugated. That automatically makes it non-aromatic. Nice.
Yeah. And then I said that the next one after that was aromatic because then you now you have like the lone pair to.
Uh-huh. Yep. Nice. Mm-hmm.
And then I said the last two were not aromatic.
Yeah, so this one is non-aromatic because this is not fully conjugated. This one here, it is cyclic. It is planar because this is an sp. Oh, this is a carbocation right here on that carbon, a positive charge. Right. Carbocation. So that makes that carbon also sp2 with an empty p orbital. It's empty because there's
Okay.
no electrons there, giving that a positive charge, and it is fully conjugated because we could do resonance there and have the carbocation go here, and then do resonance again, have the carbocation go there, do resonance again, have the carbocation go here. So we could do resonance all throughout the ring here.
Hmm. Okay, so this would be aromatic.
Yeah, this would be aromatic. Three pairs of electrons. 1, 2, 3. Odd. aromatic. Nice. So here are some oddball ones. Let's say we have a carbonyl in the ring, which is a carbon double bond oxygen, right?
Hmm.
We have to draw the resonance structure of the carbonyl to see what charge it gives on the carbon part of the ring, which is a positive charge right there. And then from this structure here, this is when we use the table to determine if it is aromatic, anti-aromatic, or non-aromatic.
Okay. So would this one be anti-aromatic?
Yep, anti, because it is cyclic, planar, fully conjugated, and only two pairs of electrons are doing it, which is an even pair. Nice.
Yep.
So the other tricky one is not tested because it is really hard to tell if something is going to be planar or not. In all of these cases, we just assume that it's planar because all of them are sp2 hybridized. But there are some weird examples that even though all of them are sp2 hybridized, they are not planar. And the reason why is because of steric hindrance. And I'll show you an example of that. A very iconic example is this molecule here, where we have this structure that is fully conjugated because all of these atoms here are sp2 hybridized. It is fully cyclic, and we assume in the problems that we do, like at least for the series, it says like assume all of the structures are cyclic, but this
Mhm.
structure here is not cyclic because we know that there are um going to be hydrogens on these carbons here, but they're so close to each other, right? That there's a lot of steric hindrance going on here. Steric hindrance right there, where one of the hydrogens is actually going to go up into the plane, and the other hydrogen on that carbon is going to go down to avoid touching each other. Since they are so close to each other, they don't want to like uh do that, so they're gonna smudge the ring into like a boat shape basically. So this is not planar. But when he gives you problems on like determining if this molecule is aromatic, anti-aromatic, non-aromatic, I think he will probably make you assume that it's cyclic, maybe. I don't know yet.
Yeah, I mean we'll see tomorrow.
Yeah, we'll see tomorrow. Right. Because steric hindrance. And there are some other molecules like that are fully conjugated, sp2 cyclic as well, but not fully planar because of the steric hindrance thing here. Yeah, and he'll go over examples of that tomorrow, like these structures here where they are not planar. Right. Okay, let's try the worksheet. Let me put the table nearby. Okay. Yeah, let me just tell you the ones that I just went over, the ones that are not planar. Uh, this is the one that we just did, which is not flat. Uh, this is also not flat. It's gonna have like this kind of boat shape. And this is also not flat. Yeah. So that makes all of these non-aromatic. These three here, non.
Okay.
But the other ones, yeah, we could do. We could assume everything else is cyclic. I mean, everything else is planar.
See. Um Did I draw the first one down? Oh, I didn't draw the first one down. Correct. The first one would be 1, 2, 3, 4. Would be, is it anti-aromatic?
Anti-aromatic. So let's see. How many pairs of electrons did you say are resonating?
I said 4. Wait, let me look at the NH. 1, 2, 3, 4, 5. Oh, wait, no, because that one doesn't resonate because there's the, okay, so it'd be aromatic because there's 3.
Yeah, yeah. This is in an sp2 orbital. This is in a p orbital, and electrons in the p orbital are resonating. So that electron is resonating, that those electrons are resonating, and these electrons. Odd pair, aromatic. Okay. That pair right there on a nitrogen that is already double bonded to a carbon is not resonating. So we don't count that as a pair.
Yeah.
Right. Nice.
Are the carbons with the lone pairs also sp2?
The carbons with the lone pairs are also sp2, yes. Where the p orbital is full. It's full of a lone pair of electron.
Okay, so that one would,
NH.
I'd say that one would be aromatic then.
Yes, aromatic. 3 pairs.
This one is anti-aromatic, the third one.
Nice. 2 pairs. Because there
Uh,
are nothing
yeah.
there.
The other one is non-aromatic because there's the sp3 carbon, so you can't resonate.
Nice. Nice.
And then it would be, the next one would be anti-aromatic because all sp2 but even.
Right.
And then the last one would be aromatic because it's just one pair. Yeah.
Yeah. One lone
Uh,
pair, odd, and we have this one.
would this be the same case where the oxygen's lone pair doesn't resonate as well?
Yeah, same case. Where does it resonate? Because that oxygen is already occupied with that double bond right there.
Okay, so then this one would be 1, 2, but that double bond resonates, right?
Yeah, that double bond resonates.
So this would be aromatic.
Yeah, nice. This one, no resonance. Yeah, you got it.
Cool.
Mhm. Yeah. Oh yeah, there's also this last one here.
Oh, on the bottom.
That is cyclic. Oh, I mean that's planar.
sp2, sp2, sp2. Okay, it's all sp2, and then 1, 2, 3, 4, 5, 6. This would be anti.
Yep, anti, because we have 6 pairs of electrons, which is an even pair, anti-aromatic. Yeah.
Yeah.
Okay. That is good. That's the end of that worksheet. And that is also end of the first topic of the next chapter, the aromatic, anti-aromatic, non-aromatic. The next section that we're gonna talk about is like the electrophilic aromatic substitution. Um,
Is there any like
uh,
different type of nomenclature stuff, or would it just be like just like alkene nomenclature that you follow?
alkene nomenclature, and also there are new terms like ortho, meta, para from the benzene ring.
Do you include
Um,
those like kind of like how you'd include like RSEZ before the like as a
mhm.
prefix?
Yeah, you include that before, like ortho. You don't have to write out the whole word like ortho, meta, para. You could write O, M, or P as an abbreviation for that. O
Okay.
for ortho. Yeah. Uh-huh. Okay. Where let's say we had some kind of sub benzene ring here with some kind of random substituent. Right. 1 carbon away from that substituent is the ortho position. 2 carbons away from that substituent is the meta position. The one parallel to that substituent is the para position. And in 118C, the carbon directly holding the substituent is called the ipso position. It's more for 118C. And this is any kind of random substituent, any group. Okay. Right. So let me give you the general a general reaction for electrophilic aromatic substitution, where a lot of reactions that this chapter follows is this general pattern here. Electrophilic aromatic substitution. You could abbreviate this as EAS reaction as well. So let's say we have a benzene ring here that is aromatic and stable. Oh, we really talk about the stability of these things. Aromatic is going to be the most stable out of those three. Non-aromatic is the second most stable, and then the least stable is the anti-aromatic structure. And that has to do with like the uh
Is
anti-bonding orbitals, like some
okay.
kind of orbital molecular orbital stuff that I'm not too familiar with. Right. Right. So let's say we have some kind of electrophile floating around, right? These carbons here of the benzene are nucleophilic because there are double bonds in here. Think of it as like the alkene chapter. When we do resonance and push that double bond to make a lone pair on that carbon gets a lone pair of electrons, making this carbon have a positive charge.
Yeah.
One of the carbons here can attack the electrophile to give us this right here, where the electrophile is bonded to that carbon, and we have a positive charge on the other end right there, right? But that is very bad, what we just did, because we started with a stable aromatic benzene ring, but once we did that, we broke the aromaticity. Aromaticity is broken. It is no longer aromatic.
Yeah.
That is that is not good. So what we could do is we could reform the aromaticity by doing an E2 reaction. So the hydrogen that we are going to get is the hydrogen here, where some kind of base, where the base would be given in the reagent for the future reactions we're going to do in this chapter. Come back to grab that hydrogen and form a double bond right there, which will reform our happy, stable benzene ring here with the electrophile still attached to it.
Okay. And then you said the bases we mentioned later. So is it different?
Yeah, it's
It's
different for
different
every
bases, right?
reaction.
'Cause I remember and it's not like the bases we dealt with before because I forgot who mentioned it, but like the benzenes only react with like certain things. So they
Yeah,
probably have
like
this, they
catalyst,
have
metal catalyst, acids, like the reactions, they'll go over that in depth, but this is different for different reactions. Yeah. Right.
and then I mean, I guess I'm looking like ahead, but is there
Mhm.
like kind of like a Zaitsev Hoffman thing, like where if you wanted to have like the double bond place somewhere else? I mean, I guess you couldn't because it's you're only
There is
really
something gonna be like that. Well, you know how the Zaitsev Hoffman had to deal with the regional selectivity where we want to make that like a
yeah.
more or less stable double bond. For
Mhm.
benzene ring, it's gonna have very similar regiochemistry things where we have EDGs and EWGs on it.
Okay.
Where if we
Okay.
have EDGs on it, the reaction we put, the electrophile would be like at a certain position, like either ortho, meta, or para. If you put the EWG, that changes things. That changes where
Mhm.
the electrophile will go. And we talk about those as directing groups. Like an
Okay.
EDG directs the electrophile to go in the ortho and para position. And I'll go over that too. And an EWG directs the electrophile to go to the meta position. So we could like direct where the electrophile goes to on the benzene ring, depending on
Okay.
the group.
I
Right.
see.
Let me explain that right now, actually, because I think yeah, we could go over that, like the directing group stuff, like the ortho para director, meta director, right? So let's say we have this. Wait, actually, let me just give you the general concept. EDG, ortho para director. EWG, meta director, right? Where the only exception for EWG, this is the only exception. are halogens, chlorine, bromine, iodine. They are EWGs, but they are ortho para direct there. And we'll go over that as well. Okay. So let's say we have this benzene ring right here. And we have this EDG OCH3 right here with lone pairs of electrons. This EDG can donate electrons directly through resonance like that. And I'm just gonna draw these resonance structures. And then I think you could follow along where like the arrows are going to.
Yeah.
Yeah, this is the last one, last resonance structure. Right. Do these resonance structures make sense? Like how I got to these here?
Yeah. Yeah,
Right.
it does.
Where you know how EDGs, they put negative charges into the benzene ring, they donate electrons into there. What positions do you notice the negative charges are on relative to the EDG group?
They are ortho and they're para.
Right. Ortho and para, making them the best nucleophiles in the benzene ring. Since they are the best nucleophiles, that's the carbon that attacks the electrophile that we went over when we went over the general reaction that attacks the electrophile. These are the carbons that attack the electrophile because these are the carbons that are the best nucleophiles with a negative charge.
Okay.
That's why
So,
EDGs are ortho para.
okay, I see.
And this is just like the general patterns for all the reactions we're gonna do. Like if you understand like these general patterns and the behind the scenes, then learning the reactions is gonna be so much more simple because it's gonna follow the same exact principles over and over. It's just different reagents and different stuff, but
Okay.
it just follows this whole concept here.
Okay. Is the
Right.
benzene chapter like in general, like would you say simpler than chapter 14?
Yeah, yeah, much more simple in chapter 14. Like this is my favorite chapter, the benzene chapter in Monicine B.
Okay. Okay,
Yeah.
cool.
Right. And the synthesis for this chapter is like so good too.
Okay. I
Where
mean, my only does like 2 steps, so we'll see
Oh
how
yeah,
like
two step synthesis. I know.
in-depth
Right.
his synthesis is.
Yeah. Right. Let's say we had an EWG instead, where I'm gonna draw the resin structures and then let me know if something does not make sense here. Right. Pascal's like synthesis is easier than Levin's, but his vocab is harder than Levin's.
Yeah.
Yeah.
I don't know if I like that trade-off, to be honest.
I know. You gotta really read the textbook and understand like things conceptually.
Yeah.
Where that EWG is actually withdrawing electrons from the benzene ring, not donating. Okay, last resonance structure. Here. Yeah. So do these resonance structures make sense?
Yeah.
Yeah. Where EWGs, they create positive charges on the ortho and para position relative to the EWG. That makes the best nucleophile the meta position. Even though there's no charge there, that is a better nucleophile than the positive charge. Because
Yeah, I see.
Mhm.
Yeah,
Right, right. So that's why there are meta directors. They will attack electrophiles at the meta position relative to the EWG.
okay.
Uh-huh.
All
And
right.
there are relative strengths of EDGs and EWGs as well, but we'll go over that next time.
Sounds good.
Yeah.
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 All right. Thanks for going over those. It helped. I appreciate it.
Yeah, no problem. No
All right,
worries.
take.
Yep. See ya. Bye. Hey, Zinyan, how are you?
Oh, good.
Did these help like the things I went over today?
Yeah.
Did you have any questions on it?
No, I followed.
Okay, that's good. That's good. That's good. See. Did you have any other questions on other things besides this, like the previous chapter, what we went over today, Diels order, alkynes, conjugated dienes, any other questions?
Uh, maybe, but like it was too much, too many
Oh,
stuff.
too many things today.
Yeah.
Yeah, you need a mental break. You need a mental break.
Yeah, but like I think it makes sense. It
Uh-huh.
looks easier than the stuff we went over
Yeah,
before.
yeah, definitely is. Like this benzene stuff is so much more like it makes much more sense quicker, much more intuitive than the Dio's other stuff.
But we're still not in the benzene chapter,
Mm-mm.
or we're starting it already.
Starting tomorrow, the
Oh,
benzene
okay. So like
chapter.
chap is that the last chapter?
Chapter 15 is the last, or chapter 16 are the reactions of it. So chapter 15 is just like the introduction, like aromatic, anti-aromatic, non-aromatic. And then I think chapter 16 goes more into reactions and mechanisms of
Okay.
it. Uh-huh.
Okay.
Ooh.
We'll
Yeah.
wait to see how
Yeah.
he does this tomorrow.
Yeah. If you go to lecture tomorrow and then like he goes over this and then like you understand it, that would be so good.
Yeah, I will. I hope I
Yeah.
will.
I
Yeah.
see. That's
Thank you
good.
so much.
No problem.
Okay, have a good night.
Yeah, you too. See ya.